And starting off this lineup, we have Team 2046 giving a talk on their CNCing process. We're calling this workshop CNCing Bare Metal. And with us, we have Eliot and Ethan from 2046. So we're going to hand it off to them. Feel free to ask questions in Discord and in Twitch. And at the end of the workshop, we will try to ask them. So without further ado, take it away.
Hello, everybody. So my name's Ethan Bertrand, and with me here is Eliot Quincio. We are the fabrication leads for Bare Metal 2046. And today we are going to be showing you guys just a little bit of what we do. So if we go over here to the presentation.
Okay. So in our presentation, we're just going to discuss methods that we at Bare Metal use to stay organized and efficient for our fabrication team. Now keep in mind, this may not work for your own. This is what we have found that best works for us. And we're just going to go over some of the processes and methods that we use to stay organized and efficient as a team. Do you go next one, Ethan? Thank you. The first thing is our use of integrated CAM and CAD. We use Autodesk Inventor Professional 2021 and Inventor CAM 2021 of the same edition. We use integrated CAM just because it allows quicker transitions and changes between our design and manufacturing processes that allow us to fix any errors that occur in our CAM or in our designing periods. Now, some teams use SolidWorks. We use Inventor. We just have been using that for a while now, and we're more familiar with it. So that's why we have stayed with Inventor rather than moving onto SolidWorks. And having an integrated CAM really helps us just because we can always fix parts that need to be fixed, either if designs change or if manufacturing changes as well. And for the next couple of slides, we're going to have videos of examples of our integrated CAM and an example of how we CAM a specific part.
So I'll play this one without. So in here, you guys can see this is the interface of Autodesk Inventor CAM. I'm not familiar with SolidWorks, so I don't know how this differs, but in this, you can see how it has a CAM section. So for the actual part, we are actually able to go into the CAM for the same design, and we can just easily switch between the actual sketches and the extrusions and the actual CAM. So in a minute, I should switch over into the CAM. All right. And here we have all our operations. We have the simulate button, we have the setup, and then we have all of our actual toolpath buttons. So we can easily, if some hole changes in our design, for instance, right here, if this hole was moved, we could easily edit it, which is very useful for us. But for everyone at home that uses SolidWorks, there is a integrated CAM version of MasterCam, so that could work for you guys as well. That's just a quick video on that. And then this is a 10-minute long video. I might skip some parts depending on how repetitive it is, but I will let it play.
could you guys go through a little bit and talk through what's going on in the video? I think it would help out.
Yeah, sure.
Of course. Thank you.
Do you have any questions? Are there any questions in the chat asking about any operations? Because that way.
No,
you
I
can
think
talk about
it would be useful just like what's going on the screen, kind of just talking through what you're going through, the process of why you're picking certain buttons and stuff like that.
Sure. Okay.
Of course.
We have a slide for that. So would you rather me just go to that slide and talk about how we use?
Sure. Yeah.
Okay.
Thank you.
So on bare metal for our cam, we use standardized measurements. So in the actual video, you guys saw how the holes were 0.196 inch in diameter. That's because that's the most standard size screw we use, because we want to use the holes that we have the tools for. Because if we have a hole for like 0.22 inches in diameter, that's really awkward to cam for us because we don't have a 0.22 drill bit. Because for then we would have to use a number 2 mill bit, which is 1/8. So we'd actually have to mill out. We'd have to use a 2D contour for a hole for a screw, which is really inconvenient for fabrication. It can slow down the whole process because if new kids are on it, they'll be confused. So we want to use standardized measurements in every single part of our cam. We want, no matter what member cams apart, we want it to be exactly the same. That way we reduce our margin for error. And then we also we don't use awkward size stock, so we only like to do 1/4, 1/8, and rarely 1/16. We mainly only stick to 1/4 and 1/8 inch for stock on plate, and for tubing diameter and for tubing thickness, we normally only use 1/8. We uncommonly will use 1/4 inch thickness for tubing. And then as well as this, you'll see that we change our cam depending on what machine we use. We will change the speed at which we cut depending on what machine we are using, and this is it should be what you guys should do as well, because not every machine cuts the same way. Not every machine has the same like x-axis like travel distance. So you will see that in the cam, because in this we are doing this on our Haas BF3 SS, so that allows us to cut everything slightly quicker. So if I just go to okay, this is our end cut. So what we are doing in this is we are cutting right here at the end of our part, because we only face one side. Because we have a faced stopper that we press against this side of the actual part in a vise, because that way if we're making multiple parts, we just slide these in and out. Because if we have to make maybe say 4 of these parts, we don't want to have to redo the X, Y, and Z axis every time. If we want to do one setup with our probe, and then we want to be able to do 4 of these exact same parts. So we face this side, and by facing I mean we put this into our vise on the manual mill, and we take our, I think it's 1/2 inch diameter end mill bit, and we just take off maybe a 1/16 of an inch, and we do it very slowly, and we will maybe do 2 passes, because that way we get rid of a lot of inconsistencies in the actual face when we use our chop saw or whatever we're using to cut this stock. And by doing this, we make sure that this is perfectly flat, or like near perfectly flat, so that way when we put it against the stopper in our actual vise in the Haas CNC mill, it will be at that exact point for every single part we do. So, and then because we face this, we always cut our stock just a little bit longer. So if this is say 20 inches, if the part is actually 20 inches in the CAD, we will cut this to about maybe 21 or 22 inches. And then, so then while we are actually machining this part, this stock will be around 21 inches when we need it to be 20 inches. So then we will see how we use this end cut. We saw how we use this end cut where we just take the tool number 4, quarter-inch end mill bit, and we just cut along this side. And then for every time we flip this part in the actual vise, we cut. So basically we cut each side when it faces up. So that way when this part comes out, it's exactly 20 inches. So it may be 21 inches, 20.5 inches, 22 inches, whatever size. We always want it to come out 20 inches. So we could have stock. So if we have 4 pieces of stock that we're trying to turn into 4 different of these parts, we face one side on each part, put that face side perfectly flat against this little stopper that's in the corner over here, and then we just do an end cut. So you could have varying lengths of stock, but as long as one side is faced and we do the end cut operation on each face, then we get the equal length of parts every time. So that's why we do end cut, and that's why we face our parts first, to ensure that our parts are actually equal length even if we have varying stock. So we were and then here I will play it with volume and then I'll pause it afterwards so I can talk about it. So what I'm doing here is we like to run this operation that we call Hostiburr. It's where we take a spot drill. We use tool number 6, but a spot drill, I think it was with was it 45? It was a 90-degree spot drill. So we use a 90-degree spot drill, and we go along every single contour except the outside. We go along every contour that we cut. So we would go along these, and then we would go along our end cut, because what this does is it gives a nice chamfer, and it saves our assemblers a lot of time deburring, because for other parts they would use an actual hand deburr and they would just scrape it, and human error made it so sometimes they could mess a part up, because if they went really hard they would just take away too much material and we would have to redo the parts. So we've learned by doing Hostiburr, we save a lot of effort and time, and it gives our assemblers less work so they can work on more important things. And this is especially important on our bearings, on our bearing holes, because if an assembler goes too hard with the deburr on a bearing hole, it's ruined. The bearing hole doesn't fit the bearing perfectly anymore, and essentially the part that took us maybe like an hour to make is ruined, which really sucks when you're in a huge rush and you have to get parts like done, and then it's just ruined because of human error. And then I don't think I talked about this, but on our end cut, see how this feed per tooth is 0.0025? That is too fast for an end cut for bare metal, because we've had instances where we might shatter a actual end mill bit because if you're going through a 1/4 of an inch tubing and you're hitting this wall right here and you're going at the max like feed rate, your bit you can mess up the part and you can mess up the bit. So you see me, so here I add a 1, so I essentially cut this in half. I slow it down by half, goes from 90 to 45 inches per minute, to ensure that we do not damage our bits, because damaging a bit in the middle of a busy operation is extremely bad. And then for here, you see me selecting we select the tops of the holes because you don't want it actually going inside the part. You just want a surface level contour. And then you want to do a slight offset. That's fine because I selected the top of the holes. Selected contour is good because you don't actually want to dig down in the part. You just want to do the teensiest. So here, this is what this looks like for Inventor. We have a chamfer option. So we have the chamfer width. I put it incorrectly in here, and I can't remember off the top of my head because we haven't had to use chamfer in a while. We haven't had to do Hostiburr in a while, but we do a very small actual deburr because we don't want to be taking off too much material. In the simulation later, you can see how much material this actually takes off, and you can realize like how that would just gouge out your part. So you can see right here when I play it. That is too much material. You probably want it to be half because you want the slightest deburr, so that way it's not sharp on the top, and it makes it look really pretty, which is aesthetics are always important. And then in order to save time, we do this fancy little trick of just duplicating the setups and deleting all the previous things, or just keeping them. Because on a simple part like this where you just have holes on each side, you can just duplicate it and just change the tool paths and change the axes. So I will let this play. You saw how fast that was. Instead of making a completely new setup and having to go through all the silly, like changing the stock lengths, we just did it in maybe 2 seconds. So those 2 seconds saves a lot of time when you're going through a bunch of parts. As well as this, we use the X and Z axis because when we have this against a stop, it's kind of difficult to use our probe on this side, and sometimes if a part is really long, we can't actually go all the way out over here to do the y-axis. So we like to do the z-axis and x-axis just because it's right here, and it also might be because we can do x-axis on a vise where you can't really check the y-axis on a vise, because if this is clamped in a vise, the far end of this part, so this edge right here and where it touches the vise, is almost the exact same x-axis. So that's why we do z and x-axis. And then you saw right there, instead of having to go up here, drill, tool 6, change bottom height, change breakthrough, because I duplicated it, it was just cancel, click. And that's also extremely useful because if we finish camming this part, we save it, we upload it to Perforce, and a designer checks it out and changes the location of a hole, say he maybe adds another hole right here, or he moves this over here, all we have to do is download the part, go into here, double click it, go to select faces or geometry, and then maybe just control click on one of the holes to delete it, or just exit out, delete all the holes, and just re-click them. So instead of having to export this, like export the faces, go into Mastercam, all we have to do is maybe do a few clicks, and it saves us so much time, and it gives our designers so much extra time to actually work on parts. So and you saw how easy that was in maybe like 10 seconds. Our second setup and our second face is done. So And the reason we do an adaptive for these is because a contour, it might just be too fast, and we could cut the feed rate down, but we prefer to do an adaptive first and just roughly cut out the shape. And then you'll see that we do a derived operation with the same tool bit and just slightly faster, and we just clean up the edges. We found that that gives us a better cut, like better accuracy, better precision, just for the actual cuts. And this is extremely important on bearings, because on bearings, you don't want to just go in and just go guns blazing, cutting all the material out. You want to do like a slow adaptive, cut out the rough shape, leave a little axial material left, and then with contour, you want to go in and actually cut out the rest of that material. So and we do the slightly over the actual thickness, because if you cut straight to the thickness, you might have like a little lip right here of this super thin material, and that's just extra work for assemblers. Just takes extra time to cut it off, so we just clean cut. Right, so my bad. We actually don't do any axial stock. It's the radial stock to leave, where we do this tiny amount. And then we only do this for really bearing holes, but I kind of just do it out of habit for every like adaptive. It doesn't really take any extra time. It's just, good to be in the habit of it. So in case you do a bearing hole, you're just in the habit of doing it. And then in the direct operation, you do the same number, but you do a negative. So that way it cuts it to the exact radial length. We have found that the most common error for cutting out a adaptive or contour, if it does not generate, look at your ramp first. If the ramp degree is too high, say if it's like 4 degrees, then it's like swirling. And if you're using a big bit like I am, I'm using 1/4 inch, and you have a high degree ramp helix, then it's not going to generate, because it's saying, sorry, you can't do that. Your ramp's too high, it's going to cut. So, and a low ramp like this is good. It takes the machine a little bit longer to cut, but in order to make sure that you don't you're not going super fast into the adaptive, or you're not cutting into the walls, it's good to do this. Or you can do 0. I believe on bearings we do negative 0.006 inches. That way we just make sure that's like a perfect fit. I don't think we actually do 0. This was a mistake on my part. But since these aren't bearings, it doesn't really matter. And that was the just deburr, see how we do it on everything. And then this is the final setup. And And also that button was flip X axis, or just flipping your axes. You sometimes need to do it just because the setup might be a little wonky and just might have your X axis going the other way. You always want it going, if you're looking at the top down, you want the X axis going this direction with an arrow, Z axis coming up towards you, Y axis going this way with an arrow. You saw there, I didn't need to generate it. I prefer to generate it just because, I don't know, I find it good luck. I haven't really, ever heard anyone say otherwise, but I always generate my parts. Also, this button stock is extremely useful because it will cut away green. So basically this green is just the stock, and it will cut away wherever the bit hits, and that's extremely useful if you're trying to look at a part to see if it cuts wonky. So.
And this integrated cam allows us to see if there's any errors within our machining. It will show a bright red color on the bottom of the screen if it's hitting a part that is not supposed to be, or if it's hitting a place on the piece that is not supposed to be machined out.
Right, and like Eliot said, we got a red error. So if this tool bit went all the way in and this was hitting the chuck, or the tool holder, sorry, it would give us a red, and we'd be like, okay, we got to change something, and it's extremely useful because if you're on a vise and you're having a facing tool, and that facing tool hits the vise, oof, that's not good, especially if the vise is hardened steel,
And the same process works for fixture plates on a bed of a machine and plate parts. If you have plate, the software allows you to see where the tool path of the tool is going to be, and if you need to drill out and fix in screws into the fixture bed or the fixture plate, it will let you know if you're going to be hitting those screws, so you can have a better adjustment of the piece.
And if you guys are unsure what a fixture plate is, it's basically a big slab of solid aluminum that is machined out to allow screw holes, to have threaded screw holes and places to attach it to the actual bed of a mill. And we use a large fixture plate for our Haas plate because we've had really large plate that we've needed to machine out. And you have to be so precise with your machining, because if you're off by a few thousandths or a few ten thousandths, then you hit your fixture plate, and bad news bears, you've now damaged a very expensive piece of equipment. So always check your cam, always run a simulation, always get peer reviewed, because if you're in a busy build season and you're hammering parts out and something's messed up and a part is damaged, or a machine is damaged, or a drill bit, or hopefully the machine doesn't get damaged, but if a tool is damaged, then you need to replace the tool, you need to recut the stock for the part that you messed up. So it just cuts a lot of time away from manufacturing, and more so it cuts a lot of time away from your design, because the purpose of fabrication is to give as much time to our designers as possible to design the best possible product. So anyways, take it away, Eliot.
So aside from the cam, it's also important just that we stay organized outside, especially on preparing parts and pieces and the stock to be manufactured. Um, so one of the things that we do is we utilize working parallel, which allows us to prepare parts, machine parts, and cut parts all in the same time. So if we just have finished a part within in a machine, we are now ready for another part to come out, to be machined. It allows us to save more time, not just for fabrication, but also for design and assembly even. It just allows us to be much more efficient and effective because we have a constant supply of parts that need to be machined out. The room is something new that has just recently been added to our bare metal shop. The room stands for Rack of Organizing Materials. In this, it helps us to keep track of all of our parts and to just stay organized, because on the rack of or on the room, we have each shelf is designated for one type of part. If if a part could be plain stock that needs to be faced, cut, or prepared to be machined, another shelf would be for our stock that has already been faced and is ready to be machined. A third shelf would be the pieces that have been machined, and then our last shelf would be for pieces and parts that are ready to be powder coated or ready for assembly on a robot and its subsystems.
And then one thing I don't mention here is that our parts are post-processed after, well, we mentioned how assembly takes them, but so we have a shelf for parts that are machined and ready for post-processing. So basically we put the parts on the second to top level, and then our assemblers, when they see parts go on there, they will come over, take them, scrub them down with some Brillo pads if they're powder coated, clean them, dry them, wash them, all that stuff, and then put them on the shelf ready for powder coating. And another thing we do that's extremely helpful for our manufacturing process is we label our stock. So if we have two similar pieces of tubing stock, but they're both different parts, we will actually label them with the last 4 digits of the G code. So we will label them maybe like 1, 2, 3, 4, and then the second, and then we rotate it 1, 2, 3, 5, 1, 2, 3, 6, because each face is a different operation with a different G code number assigned to it.
And that can be different sometimes. If a piece has the same face as other faces, we can just use the same operation from time to time.
But that's more into the complicated side of the manufacturing process.
So for new members and how we train them, we first introduce them to smaller machines and simple hand tools, such as bandsaws and sawmills and small mills, even drill presses also. Uh, After introducing them to smaller machines, we will teach them CAM for tubing, plate, and angled stock on Inventor Autodesk CAM 2021 that we have. And this is going to actually get them started into using our more complex and main machines, such as the Haas and Tormach mills and lathes. But this year is kind of different, especially with COVID. We've been using online teaching instead of hands-on physically in the shop training. We've been using Google Classroom, and we have been having meetings on Zoom that just revolve around CAM and teaching our members correct ways to do CAM and what they need to fix in their already known.
And with COVID, it's extremely difficult to actually train new members on machines or get them interested in new machines, because we don't have access to our shop. Well, we don't actually have access to the school at all. So there's almost no way to actually like get videos, because what we think would be good is to get videos of the machines running and like a vlog. Basically, if anyone out there has like the opportunity to like take vlogs, that is what we would do. So we would take like videos of yourself running the machine, but at the moment that's not possible. So what we are focusing right now is basically what we can train on, which is CAM, and mostly just CAM, which is hard on our new members and for our returning members who want to like get into the shop and machine stuff, because working on just CAM can get really boring and just repetitive, and it's not the excitement of like basically like in-person fabrication. So that is one of our most recent challenges. And then So you saw in the video, I already talked about this slide, but standardized measurements. I already talked about how we want every cam to be like the same in like the measurements that we use. So, but then I don't think I talked about, right? So we use only a certain number of tools for the majority of the time, which is really useful because it means that you're not having to like change the cam a lot depending on what tool. I'd say our most common tools are 1/4 inch end mill, 8-inch end mill, 0.196 inch drill bit,
Your spot drill.
90 degree spot drill, and that will get us almost all of our parts. And those four, well, technically three most important, because the spot drill is kind of just an extra for aesthetic and for efficiency, but it's not necessary. But those three tools are our standard measurements for our design as well, because our designers, most of their CAD revolves around what we can machine. So, and we don't like to machine polycarbon wood because on the Haas, polycarbonate, when you machine it, even with coolant, it kind of just melts. Like if you machine it without coolant, bad idea, because it will melt onto the bit and then harden. And then you have a tool bit that you need to machine with encased in solid plastic, which is so much fun when you're when you're reaching into the Haas with some pliers, trying to rip it off. So we only really like to machine polycarbonate on our ShopBot, which is a little router, and it has its difficulties. So we might only have a few parts that are made with polycarbonate. Polycarbonate makes up a small amount of our actual machining process because of our standardized measurements and our standardized materials. And wood, I don't think we never use wood besides for prototyping. And for prototyping, we use laser cuts. So our materials and our measurements revolve around our machines, basically. Everything kind of revolves around what we can make in shop as quickly and efficiently as possible.
And for wood, we sometimes use our different machines. For wood, we used our Tormach mill, and we just slow it down a lot more than we would do for the Haas, just because it's wood and it's not as strong as aluminum.
But we rarely, and
Yeah,
by
we
rarely I
rarely
mean
use
like
wood.
almost never, use wood on our actual milling machines besides the ShopBot. And then, so keeping camp uniform, I did not hit on this in the video because, so we have templates. They are pre-programmed operations that have all the settings. So instead of clicking on 2D, like 2D cut, 2D cut, and then going through all the options and changing it depending on what material you have, you right click under whatever setup you're doing and do new template. And then we have pre-made templates that are like 2D cuts, drill, spot drill, that have all the settings cut. And and then you just change the settings. You just change maybe like 1 or 2 settings, depending on the thickness of the actual material. And then instead of changing like multiple settings, it's super quick. So in a part that might take you like 5 minutes, it could take you like as soon as 1, which that 4 minutes or that 10 minutes adds up so much. But we prefer not to do templates because, especially with our new members, because we don't want them to get used to not actually going through the cam and understanding the settings. We want all of our members on Fabrication to understand what all the important settings mean, what to look for, like to understand that it's right. Because if a user is just using templates and then those templates are out of date, and then we're using different settings, those parts will be different than what our new standard is, which can hurt if you don't catch it. So, but the most useful template is probably the deburring, because you already have the offset for the chamfer set and you just get to go through the actual deburr really quickly. And then I mentioned earlier that we do a peer review system. So all of our members, all of our fabrication members know what to look for. At least all of our returning and advanced new members know what to look for. So instead of coming to me or Eliot every time, because we are busy a lot of the time, we're like on the machines almost. We're on the machines most of the time.
Mhm.
We will have our members check each other's cam and check each other's stock, because we want our members to understand the entire process of machining. So, because in the welding industry, you constantly, especially in the high advanced welding for airplanes and aerospace, they check the welds constantly to make sure that it has no deficiencies, it's not going to break. And that's what we want to do with our cam. We want to make sure that our members are experienced in checking cam, because in fabrication, understanding what to look for when something's wrong is so important, because that will save you so much worry, so much stress. And then as well as that, we have our members do sanity checks, where they just, when they put in the actual coordinate system for the part that they're making, when they use the probe and they put the origin, we have, if they're nervous, we have them just put in Y0, X0, Z1, and then it goes directly to like that point. And then you look at it and like and if it's like right over where you put the actual setup axis origin, then you're good to go. And then yeah, just we look to make sure that we look to make sure that our bits are never turning red in the simulation. It's always green. It's always good to go. You always make sure that the heights of the tool path are also good, because we've run into issues where your retract height is not enough. So you might have a part with different heights, and then your bit might think that it retracts to this height and just moves around and there's nothing obstructing it, even though there's stock like right next to it. So it might run into the stock, and that's very bad. So retract heights are often looked over, but they're also extremely important. And then fixture plates, again, you just never want to run into the fixture plate. You can always zoom in. We always do 0 point, I think the least amount of stock to leave between the actual plate and the fixture plate is 3 thou. So that's a film that's 3 thou thick between the actual, like if we're drilling a hole, we don't drill on the actual fixture plate. We do a 2D contour with tool number 2, where it goes in a helix. Or actually, no, we do bore now. We used to do 2D contour, now we do 2D bore. Because instead of doing a helix down, oh, you can't see my hand background. Instead of doing a helix down, it just goes, it bores straight into the material, and then it stops 3 thou above the fixture plate. So you'll have a really thin film that the assemblers just have to deburr. So that's what we do for keeping cam uniform, keeping our fabrication
Yeah.
uniform.
So for our size of a team, bare metal, it's a pretty large team, and it's very easy for us to lose information or for it to be misinterpreted. So what we use is we use spreadsheets, and this was designed by Justin, who was our design lead that graduated last year. Anyways, we use these spreadsheets that allow us to keep track of what has been designed, cammed, is ready to be machined out, and is in the process of preparation. Alongside with the room, as mentioned before, this does help us keep us stay organized, just because we can actually keep track of all the parts that are missing, and helps us just to keep more information and lose less. An example of this is as Ethan mentioned before, with our G code, when we write the G code of each operation for our parts on the face of a stock, or on the stock of a piece, we also implement those same numbers into our spreadsheet to make sure that we don't run those same G codes or the same piece again. So, yeah.
And to clarify, we don't actually write our own G code. We use Inventor and we post-process it. And then in post-processing, we select what machine we're going to be using, because that dictates how it's going to generate the G code. And then we take that generated G code, we name it a certain number, say like if you have a part with 4 faces, 4 different operations, you might do like 1001 for the first setup, for the initial setup, and then we rotate it counterclockwise. So we rotate it away from you if you're using tubing, and then we do 1002, 1003, etc., etc. and then we write that number on each face corresponding to the operation that's going to be doing.
And also the spreadsheet helps us stay organized with our subsystems, so we know which part goes with which subsystem of a robot, and if that subsystem is complete or incomplete.
Fabrication weekend. Sometimes fabrication week. Recently, we've been able to do fabrication weekend. We have enough manpower and machines, luckily, to do this. We are extremely grateful for all the machines and manpower we have, because we are able to do fabrication weekend. We are able to run multiple machines at once, and I know a lot of teams are not that are not able to. So for us, we are extremely grateful that we're able to do this like this, because we recognize that we're extremely lucky. So on fabrication, we have all the stock that we need for the weekend prepped. We have all of it cut, measured, labeled for the operations on it. Everything's been cammed that we're going to be cut. This is when the majority of our parts are made and assembled and post-process and all that. So,
Awesome, guys. Sorry to cut you off. We do end in 2 minutes, and there are a couple questions in
Okay.
Twitch just so you guys could answer them.
then we can do that.
Cool. All right. So I'm just going to round robin. Rick Antermarin in Twitch asks, how long does your process usually take? Don't know exactly what he's referring to, but I imagine how long does your CNC process take from CAM to end of product?
Right. So from the beginning of the CAM, it normally takes an experienced member, maybe for a simple part like tubing, maybe like 5 minutes to the CAM, post-process it, maybe like another 10 minutes to cut the stock, and then to cut the stock and face it. And this isn't optimal when you're not super busy, when you can just go through it, you have everything ready. And then another maybe like 10, 15 minutes to cut it. So from start to finish, we can have a part like in our heads ready to be cammed, finished in maybe max like 40 minutes on a good day.
And the time it takes to also machine it can fluctuate depending on how big the part is and what type of part it is.
Right.
Awesome. Okay. One last question, and personally my favorite question. If you use Hostiburring, then what do your freshmen do in their free time?
Sometimes I don't want to know. They have plenty of other jobs. So the freshmen on assembly they can still deburr it depending on the part, because sometimes we don't use Hostiburr. So if it's powder coated, we like to Brillo pad it, and then they'll have to wash it with acetone. So they're still extremely busy. And then they're actually the ones also helping to assemble the robot. So the kids who post-process eventually move on to help assembling the robot. So
And they can
freshmen
always
stay
sweep if
busy.
ever.
We make sure.
All right. Well, looks like we're out of time, and those were the 2 questions that we had. So thank you guys so much for doing this workshop. I know I learned a lot. So thank you guys again.
Yeah.
Thank
Thank
you.
you for having us.
Thank you.